Welcome viewers, in this video we will see the DC transient response of RC circuit, resistance and capacitance. Case 2 discharging. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic DC transient response of resistance and capacitance connected in series. Case 2 discharging. Charging, case 1 available in separate video. Now this resistor and capacitor is connected in series, that is energized by the DC source E. There are two positions available. The switch is S is there, position 1 and position 2. If it is connected in position 1, DC voltage is applied. If it is connected to position 2, DC source is disconnected. Right. Now we'll see what will happen during this position 1 and position 2. The switch has been in position 1 for sufficient time to establish steady state condition. So initially the switch is kept in the position 1 so that the capacitor start charging. It will give the sufficient time to get the steady state condition. Let this switch is moved to position 2 at the instant t equal to 0. Right? After some time, long time, it is position 2 is changed to position 2. Under steady state condition, the capacitor is fully charged. That is during the switching position 1. The voltage across C is E, which polarity is as shown in the diagram. Polarity is plus minus. This is the polarity plus minus. Right? So initially at position 1, it is sufficiently charging and increasing the charging, it increasing the voltage E with this polarity. Afterwards, it is moved to the position 2 at t equal to 0. Right. Now we'll apply the Kirchhoff's voltage law, KVL. What is the KVL? When it is at position 2, there is no applied voltage. So, okay, right. So it is equal to resistive drop and capacitive drop. That is applied voltage equal to resistive drop plus capacitive drop normally. But now during position 2, the voltage is 0. Right. So the resistive drop plus capacitive drop equal to 0. That is the KVL, while applying KVL or differential equation of this given circuit. The differential equation of this circuit is I into R, resistive drop, plus 1 by C minus infinite to T I dt, that is equal to 0. Here no voltage is available. So I into R plus 1 by C, this minus infinite to is split into two time periods, minus infinite to 0. 0 to t. Minus infinite to 0 means initial condition. 0 to t means after closing the switch. Right. Now we'll take the Laplace transform on both the side. So this 1 by c integral minus 0 to t I dt is nothing but E. We already discussed that the switch is at position 1 for long time. So capacitor is charging and attain the polarity E. Right. So this term is nothing but E. So while taking Laplace transform on both the sides, as I become I of S. We are converting T domain into S domain and R plus this term is nothing but E. So that E by S is clearly given here. This E. Laplace transform of E equal to E by S. Then 1 by C integral 0 to T I dt is nothing but I of S by S. Integral mean I of S by S. Differential mean S into I of S. That is equal to 0. Now we'll go for the further simplification. We can simplify this equation. So I of S into R plus 1 by C I of S by S. This E by S is brought to that side. So it becomes minus E by S. Right. This I of S is available commonly. Take outside. So R plus 1 divided by Cs equal to minus E by S. Now brought this term in the denominator. So that I of S equal to minus E divided by S, minus E divided by S, and this term R plus 1 by Cs. Now we'll go for the further simplification. So the multiply the S term inside so that it is R into S. Here 1 by Cs is there, S got cancelled. So R by S plus 1 by C. Right. Now take the R outside so that S plus, here only 1 by C is there, R is not there, so 1 divided by RC. So we got S plus A, this term, standard format, S plus A, so that we are taking R outside. Right. Now I of s equal to minus E by R into S plus 1 by RC. Now we can easily take the inverse Laplace. Then only we'll get the equation in time response, time domain. Take inverse Laplace on both the sides. So that I of s is I of t. Minus E by R is constant. 1 divided by S plus 1 divided by RC is nothing but E power minus t by RC. So based on this formula, 1 divided by S plus A equal to E power minus AT. Here A is nothing but 1 by RC. So that E power minus t by RC. This A is nothing but 1 by RC. Right. In this 1 by RC is the lambda, time constant of the RC circuit. 1 by lambda. So here 1 divided by RC is lambda, right? So that is minus t divided by lambda, right? This is RC equal to lambda, not 1 by RC. So this is not 1 by the this RC equal to lambda. So that minus t divided by 1 by RC is available here. So that 1 by lambda, right? Minus t by lambda. This 1 divided by RC. RC equal to lambda, not 1 by RC equal to lambda. This RC is lambda, right? So that finally we got I of t equal to minus EI. E by R is I, E power minus t by lambda. So this is the final equation. This from the analyzing the equation, E power minus t means it is a decreasing in nature, but in the negative region. Minus is there, so that it is a negative region, right? So the current is called a discharging current. So it is decreasing in a negative region from minus E by R to is actually increasing, but is due to the negative region, right? So minus, this is minus E by R. So this is called a discharging current. So in this video we discussed the DC transient response of the RC circuit in the discharging condition. The charging is available in the separate video, right? So subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.